Well, good evening, everybody. It's a great pleasure to welcome you on behalf of the Faculty of Natural Sciences at Keele University to this evening's inaugural lecture, which is going to be given by Professor Paul Ledger. I've got a few words I'm going to say about Paul before we start, but if Paul, I'm going to invite to give his inaugural lecture, and there will be a chance also afterwards to ask some questions at the end of his talk and mingle with him subsequently. His interest is in metal detection, so for those of you who have got that as yet undiscovered hoard of Roman gold at the bottom of your garden, I haven't asked Paul whether his research actually applies to this or not yet, but it might be worth having a word to him at the end of this evening, just in case he's got some tips on how to find it. Paul graduated with a first-class degree in civil engineering and computational mechanics from the University of Birmingham in 1998. He's got a master's in computational modelling and finite elements in engineering mechanics, and he was awarded his degree with distinction from Swansea University in 1999. And he completed his PhD from the same institution at Swansea in 2002. For his doctoral thesis, he was awarded the ECOMAS PhD Award for the best thesis on computational science and engineering. And this is an area he clearly has his research interest in. He's going to talk to us about this evening. He's held several postdoctoral positions, including at the Seminar for Applied Mathematics at ETH in Zurich in Switzerland, before returning to the College of Engineering at Swansea in 2006, where he became a lecturer. He became Associate Professor at Swansea in 2013, and in 2020 we were privileged for Paul to join us here at Keele University in the School of Computing and Mathematics. Obviously, we were just reflecting in our chat before that Paul joined us just at the very beginning of lockdown during the COVID pandemic, and in fact we didn't see Paul in reality. We knew he existed because we could see him on Teams, and he was doing a very good job, but he spent the first 2 years of his time working through the COVID pandemic in very difficult circumstances. And it's also a testament to that period, of course, that it's now 2023, so this doesn't quite feel like an inaugural lecture because you know Paul very well, but it is his opportunity in this catch-up session for him to give that inaugural lecture to us. Paul works on the interface of applied and computational mathematics, computational science, engineering, statistics. And over the last 20 years, he's established a national and international reputation for his work on the computational simulation of complex and coupled physics problems in applied science and engineering, with expertise in electromagnetism, mechanics, and accurate computational solution schemes. In recent years, supported by 3 large EPSSC grants, his research has expanded to include the computational solution of inverse problems in metal detection for security applications. So Paul has made significant contributions to the mathematical theory of metal detection and has developed expertise in machine learning and statistical approaches for the solution of inverse problems. So Paul is going to explain some of those somewhat complex concepts, I hope, to us in a way that certainly I can understand, not being a computational mathematician myself, but we're really looking forward to hearing how Paul's research is developing here, how he's contributing, particularly through those EPSRC grants, to thinking about important problems in applied areas of mathematics. So it's my pleasure to welcome Professor Paul Ledger to come and give his inaugural lecture this evening. Paul.
Yes, thank you very much, Jonathan, and thank you very much for coming to listen to my talk this evening. So, just to give you a brief overview of the sort of things which I'm going to do, as Jonathan's already done, has given a bit of a career overview, so I'll just skip through that very briefly, just saying some of the places where I've been, just highlighting that. I'll talk a little bit about computational tools, so talking about some of the underlying methodologies which I use in my research, so I'll talk a little bit about that, and I also want to talk about 2 areas where I'm applying those computational tools in my research, in terms of MRI simulations and also in terms of metal detection. And then I'll finish with a summary and outlook at the end of my talk. So I'm very fortunate to have worked with many talented colleagues, collaborators, postdocs, and students over the years. So hopefully I've listed most of those on this slide, and I do apologize if I've accidentally missed any one off. So yes, it's been a great pleasure to work with these people over the years, and I look forward to working with many more people over the years to come. I also want to express my gratitude to the funding which has supported my research over the years, which has included EPSRC funding, funding from the Royal Society, funding from the Royal Academy of Engineering, and also funding from industrial sponsors such as Siemens Engineers. So as Jonathan said, I have an education which spans engineering, mathematics, and computer science. I've studied in different places, like in the University of Birmingham, where I did my undergraduate degree, and then I moved to Swansea University, where I did my master's, and I stayed there to do a PhD under the supervision of Ken Morgan in the early parts of the 2000s. Then, after being in Swansea University for a number of years, I then went abroad and I studied and worked as a postdoctoral assistant in Switzerland, first working at the Seminar for Applied Mathematics, working together with Ralph Hibmeier for a number of years. I then stayed a further year working for the Institute for Computational Physics at Zurich University of Applied Sciences, before returning to Swansea as a lecturer and then eventually being promoted to an associate professor, working there in the College of Engineering for quite a number of years. Then in 2020, I moved to Keele University, where obviously I'm stayed to this date, and it's been a great opportunity to work with the colleagues here since 2020. So I'm aware there's quite a mixture of different people in this audience. People may have quite a deep knowledge of mathematics, people who maybe have less experience in terms of working with mathematics, and also people with maybe a computational background, and people, obviously people like my parents who have less expertise in these sorts of areas. But hopefully within this talk there will be something there that hopefully everyone will be able to get some positive things from. So in terms of my research, it lies at the interface of mathematics, computer science, and engineering. So what that means is we typically start with a practical problem, and then what we do is we introduce a mathematical model to try to describe that practical problem. That involves setting up sets of equations which we need to use to describe that practical problem. And then what we do is we convert those equations into algorithms which we can introduce to a computer using things like Python and MATLAB coding, so that we can express that in a language which a computer can understand. And then we use computational techniques to run simulations, and then also to produce results which we can then visualize, which we can use and show to industry and show to other practitioners to help them to improve either the design of a particular piece of apparatus that they might be using, or also to try to use those simulations to help them with other practical problems. And a lot of the work which I've done over the last few years is in connection with electromagnetism. So if we're going to talk about electromagnetism, and you may have heard of this person before, James Clerk Maxwell. So he's the person who came up with the set of equations which describe electromagnetic phenomena. Obviously, there were contributions by other people, but he was the first person to really join these different contributions together to express them in terms of the sets of partial differential equations which basically express electromagnetic phenomena. So there will be a few equations in the talk today. I tried to keep them to a minimum, but given that Maxwell described these equations or came up with these equations for describing electromagnetic phenomena, I thought it was important to show these to you. So what these equations do is that they basically describe the behavior of electromagnetic fields. We have things like E, which is the electric field, H, which is the magnetic field. We have B, which is magnetic flux density, D, which is the electric displacement vector. We have the J, which is the JO, which is the ohmic current, and JE, which is an external current. And there are also constitutive laws which basically really describe the particular behavior of the materials. Sometimes we also need to couple these equations to other equations as well to help us to solve problems. So what can you do with these? Well, there's lots of different important applications. I've just listed a few there. There are many more besides what I've listed on the slide. Things like electrostatics, which is used in things like photocopiers and laser printers and air filters. Magnetism, which is important for the design of magnets. It's also important in motors, in medical imaging as well. Eddy currents, which is important in things like metal detection, which I'll talk a little bit more about later on. Non-destructive testing as well. Optics and wave propagation, which is important for telecommunications, medical imaging, and radar, and lots more besides. And if we want to try to solve problems involving electromagnetism, then it's not enough just to really have a set of equations describing that and a set of constitutive laws. We also need some other things as well. And this helps us then to really set up this mathematical model that I was speaking about before. What that means is we need basically a domain that expresses where the problem is going to be solved. We also need things like boundary conditions, which reflect the behavior of boundaries. We might need interface conditions, particularly if we're having a problem with different materials. And we might also need far-field decay conditions, which basically express what happens far away from the object if we're working on an unbounded domain. And the problem is that while we have things like these Maxwell equations, we can write them down, it's, apart from really, really simple problems, it's difficult to try to write down a solution to these equations. We can't get out a sheet of paper and try to write down what the solution to these equations are for realistic practical problems. So this is really where things like the computational aspect of the work comes in, because we need to somehow approximate these equations. There's two sorts of practical problems which I'm going to look at through the talk. And one is going to be concerning looking at vibrations in coupled electromagnetic systems, particularly in MRI scanners. And the second aspect which I'm going to look at is locating and identifying hidden objects from electromagnetic signals, particularly in the context of metal detection. But before I try to do that, I also want to talk a bit about what underlying computational tools are needed to try to solve these problems. So this was really where a lot of the starting point of also my research, which has developed over the last 20 years, has started from. And so we need basically an underlying computational techniques to help us to solve these problems. And the particular computational technique which I'm going to talk about is something called basically this finite element method. So what is a finite element method? Well, if we want to try to solve mathematical models on the computer, we need to basically take these mathematical models and describe them in such a way that then a computer can understand to help us to also simulate these problems. So thinking about, first of all, a simplified mathematical model of the Maxwell's equation. So here what we have is a Poisson boundary value problem. This applies to certain regimes of electromagnetic phenomena, particularly in static problems. That's where the fields are not varying with time. Things like the electric field is not varying with time, which you have in electrostatics, and also if you have the corresponding magnetic field not varying with time, then that's a magnetostatic problem. Those problems are then described by this mathematical model. And here what we can see is these different aspects which we were talking about before, this idea of a domain where the problem is going to be solved, boundaries and boundary conditions which then reflect what happens at the boundaries, and then interface conditions which relate what happens at the interface. So this diagram here, what this represents is basically a sketch of the practical problem which you might want to solve. We might have different regions where we might have different materials. Around the outside, we might have boundaries, and we have the boundary conditions which we want to impose. And then basically we want to take this model and then move to something which we can then simulate on the computer. We said that the way in which we want to do this is through this finite element method. So the way in which this works is basically to take our computational domain and then to subdivide it into lots of smaller triangles. And then over those triangles, we're going to basically try to approximate this problem. Okay? There's a lot of work that's been done over the last 50, 60 years or so in this area. In particular, there was much work done in terms of Zenkovich and his colleagues in Swansea. So where I was working previously in Swansea University has a big group in terms of focusing on computational techniques for solving practical problems using this numerical technique. So how does this method work? Well, one of the key aspects to this method is how we build up approximations over triangles. And there's particular what's called different sets of shape functions for describing the variation of these fields over these triangles. We have something called the Lagrange family and something called hierarchic conforming finite elements. And they have different advantages in terms of how you can use them to solve practical problems. The nodal family is what might be traditionally used, and then you have degrees of freedom associated with vertices of your finite elements. But they have disadvantages, particularly if you want to have highly accurate solutions, because they basically mean that you need to write down different sets of basically functions for describing the behavior as you increase basically the order of approximation. And they also result in high condition numbers, which has problems where we could try to solve that numerically. On the other hand, if you use hierarchic versions of these finite elements, then the disadvantage is trying to interpret what we're solving for is more difficult to understand. However, they have the advantage that when you try to increase the order of approximation, you basically keep those which you already have, and you add extra functions. And this basically leads to things like better condition matrices. Common to both families is basically the lowest order approximation, which are basically just linear functions over the triangles. Then, if you want to increase the order of approximation, what you can do if you're using the hierarchic family is you keep those which you already have, and then you add extra functions associated with the edges of your triangle, and then you add, if you want to increase the orders further, then you add additional functions associated with the interiors of your element. And by doing this, you can build up very accurate solutions to problems. There are different sets of particular polynomials for you describing basically the behavior of these functions, and there are different sets available. I've listed a few there. In the past, I've collaborated with different researchers which have been developing these different basis functions and developed software for also incorporating basically the variation of these different basis functions and approximating solutions. So what happens in practice when you try to do that? And I've got a number of simple examples just to motivate really what happens. Here's a simple example. Okay, we've just got a simple square. And this is a simple example which has a known solution, so we can basically check how good does this, how accurate is our solution, numerical solution to this problem. We can check basically by measuring an error measure, so we can basically compute some measure of how accurate our solution is. One thing you could do if you want to solve this numerically would be to refine basically this finite element mesh. So basically increase the number of triangles which basically describe the domain and the non-overlapping, and basically describe the approximation of the solution. Then what you could do is you could go through and you could fix basically the order of elements which you use, and then just go through and refine the mesh. And if you did that for different orders of elements, what you get basically are these different curves. And what this reflects is how accurate is your solution against how much effort you need to do to solve the problem. And what you see here, in each case, basically you get almost a straight line graph on this log-log plot. On the other hand, what you could do is you could take your coarsish mesh, and instead you could say, well, instead of what I'm going to do is now just take my coarsish mesh and I'm going to increase the order of approximation of this coarsish mesh. then you get basically the figure on the right. And this red line represents this coarseness mesh. And what you see, there's different points here represent the increase in order of approximation. So comparing basically the performance of these two different graphs, we see that for far less degrees of freedom, we get a much more accurate solution by just increasing the order of the elements on this very coarse mesh, compared to refining the mesh and keeping the order constant. So the best strategy for this particular problem using finite elements is to use a coarse mesh and increase the order of the elements. What about a different problem? So here's a different shape domain, okay? In this case, it's an L-shaped domain, okay? And on the boundary of this domain, I'm going to impose a certain boundary condition. And this is also a problem which has got a particular known solution. So I can measure the error. And it turns out for this particular problem, then basically there is a singularity associated with the derivative of this solution. So it basically means that associated with this re-entrant corner, then there's, the solution is varying very, very strongly towards that point. And that means the strategy which we should use to solve this problem is a different strategy compared to the previous problem. Now we see that the sizes of these elements are quite different when we do these refinements. So we see smaller elements towards this re-entrant corner. And we can compare what happens when we basically keep the order constant and just refine the mesh, or where we use a combination of these different measures. So in the left-hand curve, what we see is this is basically doing P refinement on the sequence of different measures. We see that basically there's an initial improvement in terms of the error, but then basically we don't see much improvement as we keep on refining the mesh. And the same is true for the first few curves, and then we get something a little better when we go to using higher order on these different graded meshes. On the other hand, if instead now we consider the different graded meshes and we increase the order, then we see this behavior. And what's interesting is if we could find a way of combining, basically increasing the order of the approximation, also combining the different ways in which we're doing this refinement, then we would get a very rapid reduction in the error, just like what we saw in the previous case. So is there a way to try to automate controlling how we change the mesh spacing and also how we change the order of elements? And it turns out there are ways, and I'm not going to go into the details here, but I'm happy to discuss it with people afterwards. There are ways of automating how you refine the mesh and also how you increase the polynomial degree. So here we have another problem which is a more challenging problem. It has different materials. And in this particular case, I've applied an adaptive algorithm here to automate how I change the mesh spacing and also how I change the order approximation. This is a problem where I can compute the error again, and I can also, using some complex mathematics, I can also predict and estimate what the error is. So here we see two different predictions of this error. One is not a very good prediction, but the other one follows the error very closely. And this is done without actually using the exact solution. And we can use contributions to this error estimate to allow us to adapt the discretization and also get very accurate solutions. So that's fine for certain types of Maxwell problems. But for other types of Maxwell problems, then we need different sorts of discretization, different sorts of numerical tools for describing these problems. So other problems with Maxwell's equations that involve vector fields. Okay, and so this is another way basically of rewriting Maxwell equations that's appropriate for different classes of problems governed by electromagnetism. This particular equation can be applied to problems in magnetostatics, problems in eddy currents, and also in wave propagation problems as well. So for this particular type of equation, we need to use different numerical techniques, and we need to use special sorts of numerical discretizations that are different to the numerical discretizations which we've seen before. So in these particular, for these particular numerical discretizations, we use finite element descriptions where instead of having a scalar function basically describe each component of the vector field. Instead, we use shape functions which are in fact vectorial. And these arrows basically reflect the behavior of these shape functions which are used. So we can do this, just like in the previous case, we can do this for low order, and the lowest order has got a constant tangential component associated with the edges of the triangle. But we can also do this to higher order as well. And here, for example, are functions which have got a linear tangent component associated with each edge. And we can also then increase the order further by adding extra functions to the interior of these elements whose tangential component vanishes on the edges of the triangle as well. So there are different sets of basis functions available for doing this. And I've worked with different groups which have come up with different sets of basis functions. I've collaborated with these groups and developed my own software for doing this. And as you can imagine, you can put this into a computer code, and then we can use it to simulate practical problems. So here's just a simple model problem that's in some way similar to the simple model problems which you saw before. This is an L-shaped domain. Here we have a vector wave equation. We can apply the exact solution on the boundary. This particular problem has got an exact solution. It's written in terms of fractional order Bessel functions and things, but something basically which is known. That's the key thing to remember here. And that means then we can apply these different sorts of graded meshes you've seen before and combine that with doing higher order discretizations and get very accurate solutions. So this is for simple model problems which you've seen in 2D. But we can also extend all of these ideas to also solve problems in 3D as well on complex geometries. So to do that, rather than triangular discretizations, basically meshes of triangles, we use meshes of things like unstructured tetrahedra to describe complex geometries, and we also use different shaped elements as well, particularly if we are interested in things like small effects close to boundaries. You also use prismatic elements as well. So everything which we can do with these triangle discretizations, we can also do with these in 3 dimensions using these tetrahedral discretizations. And sometimes, depending on the problems which you want to solve, we might need to use discretizations for solving H1 conforming elements, basically these scalar things which we're first looking at, and also these vector fields as well. So sometimes we may need to use both of them as well. So let's now look at how we can use these computational tools to help us to solve some practical problems. The first of these, which I want to talk a little bit about, is in the context of some of the work which we've been doing over the last few years in the context of MRI scanners. And as I'm sure you're aware that MRI scanners can be used to image things like neuroimaging. They can also be used to imaging tumors and also imaging and looking for internal bleeding, for example. In terms of the basic sort of idea of what an MRI scanner consists of, it has one really, really strong magnet. Basically, the magnet is associated with a big coil of wire where you pass a strong current, and this strong current generates a really, really strong static magnetic field. Then in addition to this main magnet coil, what you also have are things called gradient coils. And gradient coils, those produce magnetic fields which vary with time. So we have a main magnet that produces a very strong static magnetic field, and then these gradient coils which produce these time-varying magnetic fields. But within an MRI scanner, there are also lots of metallic components as well. There are various shields and things which are used to then shield the effects of these magnetic fields from things outside. And basically, when you have these time-varying magnetic fields, these can induce vibrations within these conducting shields. And unfortunately, these vibrations can cause problems. First of all, they might be undesirable because then they're going to lead to patient discomfort, because the noise and things that these vibrations then generate can be alarming to certain patients. But also, they can also lead to imaging artifacts, which might then cause difficulties when medical practitioners try to understand the images which are coming out of an MRI scanner. They can also lead to helium boil-off. So helium is used to keep the superconducting magnet really cool, and that's also really expensive then to replace. So in terms of the work which we've done with Siemens Magnet Technology, Siemens Healthineers, as I now know, what they asked us to do was try to predict these vibrations that occurred within these conducting shields. And to predict vibrations within the conducting shields, just like I explained at the start, we need to take that practical problem and then convert it into mathematics, which we can then simulate. So here we're not just dealing with phenomena that's associated with electromagnetism, Maxwell's equations, but we're also dealing with phenomena that's associated with vibrations. So we need to be also able to model what happens when shields deform and the stresses that are generated in those shields. So that means we also need to combine the equations of electromagnetism with those of elasticity in this case. So we end up with a more complex description of the problem compared to the problems which we saw before. Not only have we got these sorts of curl type equations which we've seen before, which are basically associated with describing the electromagnetic phenomena, but there are also here equations which are basically describing what happens to the elastic behavior of the structure. And we can't solve one set of equations without the other. We need to solve this complete system together. With certain things which we can do to make this more efficient, and I'm not going to go into the details of how this is done, but we can set up a system in such a way to make it more computation efficient to be solved, and that's what we've done here. We've made certain assumptions just to simplify the problem a little bit. And then after solving this system, then we can recover then things like electric and magnetic fields. So how do we go about then taking that and then trying to use that set of equations as something which we can then model and simulate on a computer? Well, we need to introduce further simplifications. It's still too complicated really to try to simulate on a computer. It would be too expensive to try and do that. Well, to simplify the problem still further, we realize that in this particular application, you have very strong coils which generate a very strong magnetic field, and then the coils associated with these gradients are generating a weaker but transient response. So we can reduce the complexity of this problem by what's called linearizing the sets of differential equations about the static problem. That means that we can go from a nonlinear description to something which is linear in the time-varying fields. And that then also allows us then to reduce the complexity of this problem and also ultimately end up with a time harmonic description of the fields. When we do that, we reduce the complexity of our problem. We've reduced it now to something which is described in terms of these time harmonic fields. We can then apply the finite element methodology that I was talking about before. What that will do is lead to a very, very large system of simultaneous equations, which we need to solve using a computer. Very often, this large system of simultaneous equations we can describe using a matrix notation, so it's just a compact way of trying to write those equations. And we're looking for solutions to these equations. One of the advantages that when we apply this finite element method is that lots of the coefficients in this linear system equation are zero. It means that the matrix which you get is going to be sparse. But nevertheless, if you try to use direct methods for solving this linear system of equations, things like LU decomposition, Gauss elimination, and things like that, then you try to do that computationally. It means you need to use a really, really powerful computer with lots of memory. So that's not really an efficient way to try to do that. So you need a different way of trying to solve that linear system. Instead, we need to use iterative methods to approximate the solution to the linear system equations. And what that means is that rather than trying to take our matrix and convert it to upper triangular form, we can basically solve the linear system by doing lots and lots of iterations, basically matrix multiplication. And we can accelerate the convergence of that by using certain preconditioning techniques that basically accelerate how quickly we reach a convergence using those techniques. These are also techniques which are well appealable to multi-processor machines as well. So we can do that. Here's a simple test magnet problem. We see basically in green the different radiation shields. In red, we see the main coils. And in blue, this is a particular MRI configuration where it's only got Z symmetrical, axis-symmetrical gradient coils. I was talking about this idea of iterative solution before. Here's one measure basically of this matrix, which you see these dots basically illustrating that these are things called eigenvalues, and this is an eigenspectrum. See here that the eigenvalues are very widely spread in this complex plane, whereas in the preconditioned system, using an appropriate precondition on the same scale, now we see that these eigenvalues are all very clustered and close together, which means the performance of iterative solvers is going to be far better for the preconditioned system. And that's what you get in practice, and you can apply different order elements, just like we were talking about before. Obviously, it's this 3D problem which you now have. We can apply that then to compute outputs of interest, which are interesting to Siemens, things like the dissipated power. And what's interesting to try to compute here is particularly these resonant peaks. And the different lines here correspond to different orders of elements, just like what we were talking about before. And one of the ways in which we can reach convergence on this particular problem is to increase the order of approximation. Because of these problems, we don't have actual closed-form solutions, so we have to use numerical techniques to simulate these problems. The converged solution, which we see on the right here, we see these peaks, and these peaks are frequency with respect to this output power measure, and these correspond to resonance behavior. Similarly, also for the kinetic energy, you see a similar sort of effect where you see this resonant peaks appearing. Here, also interestingly, these dots represent some measured data that Siemens had for this particular test magnet configuration. So we're using different orders, particular discretization, different orders, and different types of shape functions for discretizing the different fields which you saw before. We can also accelerate these things as well by things called reduced order models, and I'll say a little bit more about those in a little while. Other interesting things which we can capture using these numerical simulations are these small skin depth effects, which is basically how deep an electromagnetic field can penetrate inside a conducting component. It basically measures the depth to which the fields decay to 1 over E of their surface value. So capturing these skin depth effects also requires very accurate solutions, particularly as the frequency increases, because the depth it becomes very small, so we need to use very accurate simulations to be able to capture those effects. And these are also interesting things for Siemens as well. We can also consider different sort of coil configurations here. We have transversal gradient coils, so these are then interesting again for Siemens to see how the configuration behaves when these different coils are excited. And these are these plots which we produce, then are very useful to help us to explain to the industry what's going on, what is the behavior when we solve this highly coupled problem. So here what we're looking at is, for example, the effects of the vibrations within the shields, and also looking at the fields which are obtained for exciting these different coils. So for the last part of the talk, I want to spend a little bit of time also talking about metal detection as well, which is another application which I've been working on over the last few years. So this is a different sort of application compared to the ones which you saw before. In the previous cases, they are example of what are called forward problems, where the material and the objects are known, but the fields are unknown. In metal detection, it's quite different, because in the metal detection application, this is what's called an inverse problem, where the materials and objects are unknown and limited field information is known. In other words, in a metal detector, typically what you do is you might measure certain things about the magnetic field, maybe in the form of induced voltage in your coil, in the presence of a highly conducting object. So some of the applications of metal detection, things like in security, I'm sure many of you have walked through these sort of portals in airports or other transport hubs, or maybe in terms of entering a secure environment. They're also used in archaeological digs. They can be useful also for finding unexploded ordnance and landmines. They also have applications in food safety, in process engineering, and further applications in recycling and scrap sorting. So basically what happens in a metal detector is you have a low-frequency electric current which is passed through a coil, and this generates a magnetic field. Then in the presence of a highly conducting object, this magnetic field gets perturbed, and the second coil then senses perturbation as a voltage. There's obviously Maxwell's equations behind this, so here's a particular version of Maxwell's equations, basically which is appropriate for describing this phenomena. And here, because of the low frequency and the high conductivity that are applied in this situation, then displacement currents, which are associated with wave propagation, can be ignored. But as I mentioned before, this is an inverse problem. So here, what a metal detector is doing, so you can think of this guy here with the handheld metal detector. What he's actually doing is he's measuring a voltage which is related to the perturbation of magnetic field due to the presence of this highly conducting object. And from that measurement, what you want to try to do is to identify the presence of a metallic object. But we'd like to say more than just saying that there's a metallic object there. We'd like to say something about maybe some information perhaps about where it's located, what its shape is, what its size is, what the contrast in magnetic permeability is, and also some information about the conductivity as well. So we've spent a number of years working on this together with a list of collaborators, which I highlighted on a few slides ago. And what we've done is to replace basically the system of Maxwell's equations we saw there with this simplified mathematical model for describing basically the field perturbation that you get in the presence of a highly conducting object. So what this expression here does is it replaces the system of differential equations describing basically electromagnetic behavior, this eddy current problem, in terms of a simpler mathematical model. Might not necessarily look simpler to you, but it's simpler in the sense that there are several positive things about this particular expression here. What it does is it allows us to separate out information which characterizes the object, so this rank 2 magnetic polarizability tensor. Basically, this is a mathematical object for describing and characterizing hidden objects. And it's a characterization that depends on frequency, conductivity, contrast and permeability, object size, and object shape. But importantly, it's independent of object position. And not only that, we have higher order versions of these tensors which basically provide more information about the characterization of the objects. I'm not going to talk about those today, but I'm very happy to discuss that with people if they're interested after the talk. So I mentioned already that they're independent of object position. The object position appears in this mathematical object, which is a Hessian of a free space Green's function, and the background field evaluated the position of the object. We have explicit expressions that allow us to compute these tensorial coefficients of different shaped objects, and we can do this numerically by applying the finite element technology, which we've seen before. And importantly, they separate object position and object characterization information. And we can compute these characterizations for lots of different objects. Here's some simulations that James has been doing recently, James Elgin, my postdoc. So here we have a coin which is a particularly British coins are interesting in the fact that they're made up of different materials. They're not just a solid material, they're made up of different layers which make them more challenging than you might expect to try and simulate. And here are the resulting characterizations which you can get of basically these different coins as a function of frequency. And we can compute these characterizations of lots of different objects. And ultimately what this allows us to do is to reduce this problem of metal detection to one of object characterization, location, and classification. So we want to be able to compute these characterizations of lots of different objects, and so we want to do this efficiently. And so we have basically a technique called a reduced order model that allows us basically to efficiently compute these tensor coefficients as a function of frequency for lots of different objects. This is something which we can also do very efficiently and allows us to dramatically reduce the computational time. We can also do some mathematics basically to allow us to predict the errors in terms of the reduced order models which we're using. So we can compare, for example, how well that our reduced order model compares with using basically an adaptive selection of the snapshots compared to a non-adaptive selection. So we get a massive improvement basically in accuracy. So basically to allow us to do that. Okay. So as I mentioned already, this can lead to a big reduction in terms of computational time to allow us to compute these characterizations of lots of different objects. Nevertheless, we still take advantage of using high-performance computing. We use multi-processing and multi-threading to accelerate things. We routinely make use of things like a 12-core, 128 gigabyte workstation, and we also have made use of the AWS cloud computing services. So what does this allow us to do? Well, it allows us basically to compute characterizations of lots and lots of different objects. Okay? So here was just an example of some of the different characterizations of different object shapes and things which you can see. So each of those is based on a finite element model, then to build up those characterizations of those different objects. We can also enrich this still further by using scaling results to make a much larger dictionary of different objects as well. So what do we then do with this large dictionary of objects? Then we want to go from this large dictionary of objects then to try to find hidden objects. So a metal detector, as we've seen before, measures basically perturbed magnetic fields, and then from those perturbed magnetic fields, then we can also basically work out the tensor description of those hidden objects. And we can use basically, we can use features extracted from these tensor descriptions to build up a large library which we then feed in to a machine learning classifier, because we associate with each of the different objects in our dictionary a known class, which then gives us a large dictionary. So that also ultimately means that then we can predict the likely class of a hidden object. So one of the fundamental ways that allows us to do this is a well-known result known as Bayes' theorem, which tells us what the posterior probability is in terms of the likelihood and the prior knowledge. So basically what this tells us is how likely is the class of a given object given some data. And basically we use machine learning to try to predict these posterior probabilities. So here is an example basically where we've trained a machine learning classifier built on these large dictionaries of different objects associated here with each of these different 8 denominations of these British coins. We train a large machine learning classifier to predict these posterior probabilities. What these machine learning classifiers do is they take basically that large data set and they partition it into different regions, and then given some new information, some new data, then that will fall into one of these classes and then allows you to also predict what this posterior probability is. Okay. So there are many different machine learning classifiers that can be used, and which particular machine learning classifier that you use, it really depends on the complexity of the classification problem you want to do and the available data. And there's lots of other examples of classification problems which we have in our publications. So then just coming on to briefly then the summary and outlook of what I've presented to you this evening. I've tried to give a bit of a brief summary of some of the career highlights that I've had, my interdisciplinary research at the interface of mathematics, computer science, and engineering, how I've worked with a range of different disciplines and different institutions, how I've collaborated with researchers and industry, and how I have been grateful to receive grant funding to support my research activities. Some of the outcomes coming out of this are computational tools that provide accurate computational solutions to Maxwell's equations, and then building on these computational tools, how we use them in 2 examples in terms of predicting resonances in MRI scanners, and then also how we can use the same underlying computational tools to also characterize hidden objects in metal detection. So in terms of some of the current projects which I'm currently involved with, there's currently a 3-year EPSRC funded project with the University of Manchester, and that's based on improving object characterization for metal detection at higher frequencies. There's also a EPSRC 4-year case award PhD studentship, which we currently have running with Siemens Healthineers. That's also collaborating with Antonio Gil from Swansea University. And here what we're doing is building on the work which I presented to you earlier on today, developing computational tools predicting magnet quench prediction. So this is basically when there's a massive release of energy to basically, when the causes the boil off of this liquid helium for keeping the superconducting magnets cool. So it's a really important problem for Siemens to be able to understand that and predict that. In terms of research outputs, we have an open source MPT calculator software, which has been developed together with James Elgey, and also my former PhD student also worked on that a lot, Ben Wilson. That's available on GitHub, and there's most of the publications which are written also available as open access, and there you can also then access those through my webpage. Thank you.